We're going to talk to Maximilian Beck, who is the joint first author of XLSTM paper along with Corbinian Popel. So this paper, XLSTM, stands for Extended Long Short-Term Memory, is actually an alternative architecture to the transformers architecture that we are used to. Max has been very kind to present the entire XLSTM to show how XLSTM is different from LSTM and how does it overcome the problems that are posed by transformers. We end this conversation with a question and answering session followed by Max's presentation. Welcome to the podcast, Max.
Hi, Abdul. My name is Max, and I'm happy to present on your channel now our work XLSTM. And with this work, we try to bring back old ideas of the LSTM. And we showed also that we are competitive with transformers and outperform them in language modeling. But before we start, maybe let's look back a little bit into the year before 2017. And in that time, the LSTMs, the original LSTMs, were state of the art in language modeling. And that is indicated, for example, by this paper, Exploring the Limits of Language Modeling from 2016. And the limits by then, back then, were a 1 billion parameter model, LSTM model, with only 2 layers. And they achieved like very good result for that time. But then in the year 2017, there was the landmark paper, I think everyone knows, Attention is All You Need, which introduced the transformer. And this was then much better than LSTMs. And suddenly everyone was using transformers for language modeling. And since then, of course, we had GPT-2. Language models are unsupervised multitask learners by OpenAI. They showed that we can train those transformer models on and actually only one part, the decoder only, on those massive web text data, and they learn from this text internet data in an unsupervised way, which is pretty cool. And then, of course, we had GPT-3 scaled up the model up to more than 100 billion, 175 billion parameters, and they showed that when we scale them up, these models even get some capabilities and they can learn from within the context with only a few samples, new tasks. And of course, we had the scaling laws. So now we can somewhat predict how good a model will be given a fixed compute budget and a fixed data set size. So this pretty far, and this went pretty far. And so recent transformers, like all the large language models, they use this transformer architecture with self-attention. And GPT-4, for example, Claude 3 or Gemini. But of course, there are some drawbacks of this transformer architecture with self-attention at its core, namely that this self-attention scales quadratically in sequence length during training. And for inference, it needs a large GPU memory due to the growing KV cache. And of course, many people are working in this area to make this more efficient. And there are already other recurrent neural network alternatives out. For example, Mamba, RWKV, Griffin, or gated linear attention. And Mamba brings ideas from state space models, and gated linear attention is a linear attention variant with some gates. And what we try with this work, the XLSTM, we want to revive old LSTM ideas and combine them with later techniques from modern large language models. And we show that they are competitive to transformers. Okay, but before we look at the XLSTM, let's give a short recap about the original LSTM. Here in this slide, we see the memory cell updates. And we see that we have some memory and also gates. So the gates control what goes into the memory, namely the input gate via this set, and the forget gate, the F, controls what is forgotten from one time step to time step. So in general, this memory cell updates have this cell input and a hidden state, where the hidden state is the output. and one memory cell state. I already mentioned the C, and those 3 gates, whereas the forget gate controls what is forgotten from one time step to the next, the input gate controls what goes in, and the output gate controls what is passed on to the next layer, and also to the next time step via this O. And these gates are computed with these formulas. So X is basically the layer input, and then we transform them via the weights. And what is special about the LSTM, and what also the transformer does not have, is these recurrent connections. So into the gates and also the cell input go via these R's, the previous hidden state, which is the output of the previous time step. And with this, we get the formulas with the activation functions. So the old LSTM had all sigmoid gating. So the input gate, forget gate, and output gate were all sigmoids. And the input and here the cell memory cell state, they were squashed via tanh. And yeah, this of course has some limitations. And this is the reason why people then switched to, or because of these limitations, people then later switched to transformers. And the one main limitation is the inability to revise storage decisions. And we exemplify this with the nearest neighbor search problem. So here in this problem, the goal is to predict the price of the closest value to the key. So we call this price tag to just make it a bit more simple to understand. So here, given a search key, for example, and then the input, there's the search value 2, and the price tag belonging to this 2 is 12, and the prediction has to be 12 in this case. And then the next input, for example, is 1.5, which is further away than the 2, and the price tag would be 17. So the model, the LSTM, has to memorize the 12. Then suddenly, when we get a value that is closer to our key, the 5, we have to revise our previous storage decision. So we stored the 12, and now we have to completely erase the memory and put in 14. And this is a hard task for the old LSTM. And we improve this, and that's what we show later. So in this case, we have the 14. The 14 should be the prediction. It's even closer, so now we override the memory again, and so on. And here in this plot, we see the result. So we see the transformer is basically the gold standard in this task, because due to this KV cache, which is growing with the input sequence length, it can always look back to the search key and compute the dot product between these values. And then, of course, the closest value will win, and it will predict the correct price tag, so to say. But an LSTM or an RNN in general has to memorize the whole sequence, and so it has to be careful of what goes into the memory and how it modifies the memory. And we see the old LSTM really struggles to solve this task, and the X-LSTM is very close to the transformer for this task. And we see that the X-LSTM can overcome this limitation to revise storage decisions via this exponential gating that I will introduce later. So remember, old LSTM, all sigmoid gating. Now we introduce the exponential gating, and this solves or overcomes the limitation of the storage to revise storage decisions. And another limitation of the LSTM is the limited storage capacity. So as the transformer, it grows with the KV cache grows, it has basically infinite storage capacity, because for each input we will grow the memory, and the LSTM doesn't have such a memory growing. So it has a fixed state size, and this state are basically stacked scalas. So we talk about scala memory, because each forget gate, as I showed earlier, or input gate, each gate acts on a scala. So the memory is a scala. But you're probably more familiar with the vector notation. So what we do in deep learning, usually we vectorize everything, and then we do matrix multiplies. That is what the LSTM does. But still, this storage is limited. And this can be seen on this rare token experiments, where we train 125 million parameter models on Wikitext 103. and we show the perplexity for different partitions of different token frequency. So we count how often is a token in the training data, and then we plot the perplexity only for this for a specific bucket of token frequency. And note that rare tokens must be memorized because they are so rare in the training data that they have to be that are not learned, so they have to be memorized during test time, so to say. And this we can see here that the LSTM really struggles and also fails on this task. So here we see the perplexity value on the y-axis, and on the x-axis different token frequency buckets. On the left here, the very rare tokens, and we see the XLSTM now is better, even better on the transformer, whereas the old LSTM really struggles here and is really bad. And as we go to higher frequency tokens, we see that this gap is shrinking. Of course, the tokens get more there, but still the LSTM is always worse, and the XLSTM is even better than the transformer on this task. How do we do this? XLSTM introduces a large matrix memory. We call this later MLSTM, and this solves the limited storage capacity problem. Now, the last main limitation that I name here is the efficiency problem of recurrent neural networks in general. So it's hard to make them, to train them in parallel. So to have this parallelizable training mode as in transformers. And the reason for this are exactly these recurrent connections. If you remember, there's R times H, which goes into the forget gate or input gate for the next time step. These hinder the parallelization during training time. And what we do, we introduce a new variant which is fully parallelizable, and also we make this old variant which has this recurrent connections more efficient by modifying the memory mixing, which is basically this R times the H. And okay, so now we have learned about the limitations. What is the core of our new XLSTM? And this is the exponential gating. And exponential gating has 3 gates, a normalization and a stabilization that is necessary to make it work. And those 3 gates are the same as in the old LSTM. So here are again the ideas of the old LSTM, where we have an input gate, which is now exponential. We have a forget gate, which is sigmoid, and output gate, which can be now sigmoid or swish. So the input gate now is exponential and also controls what is going into the memory. Then we have a normalization, which is necessary to make this exponential gating work. And here we basically modify the memory cell. So now instead of having only one C state, we also have a C, which is the cell state. We also have a normalizer state N. And the output will be then the ratio between those 2 states. So we add a new memory cell state, and now the output for the next layer is then the ratio of these 2 memory states. And also, to make exponential gating work, we need to stabilize it. As you might know, if you have exponential activation functions in your neural network, it's very likely to get unstable because of large numbers. So when you put in a large number into an exponential, then it grows, then the output is even larger, and you can easily reach the numerical precision range of float numbers. And for mixed precision training, it's even harder. So we also need this stabilization. So what is this exponential gating? Let's now at first recap the LSTM. Here we see the memory cell updates of the old LSTM. Green is where we have memory, and blue is the gates. And now with red, we see the modification, and also that we add a normalizer state. So now the input gate is an exponential gate. And what is the intuition for why is this better? Because now earlier only the forget gate controlled what is forgotten, and the input gate controls the input, but the input gate was limited due to the sigmoid. Sigmoid is in the range between is capped by 1. So the exponential is not limited. So if we get a new input which is now interesting, it can always upweight it higher, so it can always also override what is already in the memory and earlier. So it still has the forgetting mechanism via the forget gate, but sometimes we may want to just override it because it's so important that the forget gate cannot handle all the forgetting, so to say, and the input gate needs to override it. And this is so the intuition behind the exponential input gate. And then the output, what was here the tanh, is now the ratio between the C and the end state. What I not show here is the stabilization. Yeah, but I think this is covered in detail in the paper. And with this exponential gating mechanism, we introduced two new memory cells. On the first, the S-LSTM, and the S-LSTM is basically similar to the old LSTM as it has scalar cell states. So you see here C, N, and H are all scalars. And other than that, we apply and the Z is still the input, same as in the old LSTM. And what the main one modification also is, and I mentioned this also in the limitations, is the recurrent connections. So remember that these gates and also the input are computed via input projections and also those recurrent connections. And since we use here the scalar notation, where all these C, N's are scalars, this R is also a scalar. But what you're probably more familiar with is those vector pre-activations. So we can stack those to a vector, and then those weights, which are here just also vector, get a matrix, and also the recurrent connections are a matrix now. And in the old LSTM, this R matrix is basically a large D by D matrix. And if we now want to scale up those LSTM architectures for language modeling, we typically have like embedding dimensions larger than 2000. These matrix then gets really large. And the simple idea that we use is we make this matrix block diagonal. And this is a similar idea as for transformers with the heads. So in transformers, we also divide the embedding dimension into different heads, and then we apply the attention mechanism in parallel on each head, basically. And we can do the same. So we can view this attention as a sequence mix operation, and our sequence mix operation is this recurrence for the S-LSTM. And we basically do this recurrence independently for each head. So in between heads, we don't have memory mixing, but we have memory mixing within one head. And this is the new memory mixing that we introduced with this S-LSTM. This is the first variant. The second variant is the M-LSTM, which now has the matrix cell state. So here, instead of scalars, we have the cell state, which is a matrix. And there we get this large storage capacity that I was showing in the introduction. And you also see that the update rule now is a covariance update rule. So here we compute the outer product between the values and keys. So we use here the transformer notation. So we basically have three inputs, the values, keys, and queries here. And they are all projections of the input. And there's also no recurrent connection. And this is why this can be fully parallelized. But maybe going a bit into detail here. So the input to the cell state is the outer product of the values and the keys. And the normalizer state in this case is summing up all the keys. And then how do we get the output hidden state is by multiplying the queries with this cell state. And then we need to normalize it. And here we need to do something to make it stable during training. We need to basically limit those the normalizer to 1 so that this cannot grow because this dot product can get very small, and we also take the absolute value. And then we have here the M-LSTM. And remember, the main difference between these two variants is the memory mechanism or the memory cells. So in the SLSTM, we have scalar memory cells, and the MLSTM, we have a matrix memory cell state. Okay, both are connected through this exponential gating, and both also have an autoregressive inference, efficient autoregressive inference, because both have a limited state size and not a growing KV cache as in the transformer. SLSTM has the new memory mixing, and the MLSTM has this matrix memory with the covariance update rule. And since there we don't have those recurrent connections or recurrent weights, we have also parallel training, the possibility to have a parallel training mode. But for inference, we can still be fully autoregressive and recurrent, which makes it efficient for decoding and language generation. Okay, so let's have a look how this performs. And for this, I will focus on the language experiments in our paper. So at first, we compare our models to different other competitors on a smaller data set. And for this, we use 15 billion tokens from Slim-Pachama. And all of those models use the GPT-2 tokenizer. We evaluate on the validation set, and we used a model of about 350 million parameters GPT size. And here we see the result. So GPT has 350 million, which is lower than the others because GPT-3, or I mean, GPT, it's not GPT-3, but it's the architecture of GPT-3 basically, but scaled down. And GPT uses weight tying, and the others all don't use weight tying. This is why we have here roughly 400 million parameters. And what we can see is that compared to transformers, the XLSTM is clearly better. And here, the 1, 0 and 7, 1 means like the ratio between S and MLSTM blocks in this architecture. So 1, 0 means we only use the MLSTM, and 7 to 1 means we have out of 8 blocks, we have 7 MLSTM blocks and 1 SLSTM block. And we see that the performance is about the same, but only using the large matrix memory is slightly better and is outperforming all the other models. H3 and Mamba we categorize into state space models, and these are all linear attention variants, and also RWKV4 is a recurrent neural network, not necessarily a linear attention variant, even though those 5 and 6 have some linear attention motivation or components in it. The question is then, when we have compared all those models and it perform well on small scale, how does it scale when we scale up the dataset size, but also the model size? And this compared to recent large language models that you use in your daily life, and ChatGPT is still small, but it's also for a scientific or academic paper, it's quite large, I would say. So we train also on 300 billion token, which is the size that GPT-3 was trained initially, and which is also half of the Slim-Pachama data set. And again, we use the GPT-2 tokenizers, and we train 4 different model sizes: 125 million, 350 million, 760, and 1.3 billion, which is our largest model. And we compare those 3 models: the Llama architecture, Mamba architecture, RWKV4, and our 2 XLSTM variants. All are in a controlled setting with the same data scene, and about approximately parameter matched within these sizes. And then when we train these models, we evaluate them we train them with context length 2048, and we evaluate them on longer context. So we at first assess their length extrapolation capabilities. And here we see that the XLSTM clearly outperforms the transformer, which is really bad here due to the positional coding, which is the rotary positional coding used by Llama. And we see that when we go larger than the training length, it clearly gets really worse because it hasn't seen such training length during training. However, this autoregressive inductive bias, I would say, or that would be my interpretation of the XLSTM, makes it really strong also for this length extrapolation. And we see that the other autoregressive models, Mamba and RWK-V4, also perform better than the transformer, but still much worse than the XLSTM. So when we now use this full 60K context length, we note that we still trained only on 2048, but now we just evaluate on this context length. We see that the gap in perplexity is even larger. So, and also note that here now the 7.71, so the variant with SLSTM is slightly better than the MLSTM variant. So this is, I would say, still open for more research to look at different combinations in the architecture. Yeah, and we can explore this further, or should. Now, finally, we want to assess how this model scales when we increase the model size. And here we show the plot for 300 billion tokens. On the x-axis, you see the number of parameters now. So from left, about 125 million parameters to 1.4 billion parameters approximately. And here we see the validation perplexity. And we see clearly that the scaling behavior indicates that the XLSTM performs favorably compared to Mamba and Llama. So it still gets better. So we expect that for larger models, we still will be better than transformers or Mamba. So to summarize what we have done with the XLSTM, we have extended the LSTM by exponential gating and matrix memory. And the results show that the XLSTM performs favorably on language modeling when compared to transformers and state space models. And also the scaling laws that I just showed indicate that larger XLSTM models will be serious competitors to current large language models. And what we're working on next is we want to build larger models, of course, 7 billion plus. And for that, we need to write fast and efficient kernels for our new LSTM variants. And we also want to further explore possible application areas where the XLSTM especially excels. Okay, if you have further questions, yeah, check out the paper, look at the code on GitHub, or yeah, feel free to reach out to us for further questions.
I want to know the motivation behind starting with LSTM when everybody almost like are focusing on attention-based models. So why LSTM?
Yeah, of course, why LSTM? Because as I mentioned in my presentation, transformers, they scale quadratically, and especially for generation, so during decoding, text generation, it's very inefficient. So the longer the context gets, the slower it basically generates new tokens. And this is a really problem for applying those chatbot models. But of course, large companies, they can afford and serve those models. But bringing those models on edge devices or so will need or will require them to be more efficient. And yeah, I think recurrent neural networks at the moment are a good bet in this direction, because they have this fixed state size. And no matter whether we have a context of 10,000 already seen, each token will need the same time for generation. Whereas for transformers, it scales linearly with sequence length.
And Jan LeCun recently said that don't work on LLMs. And if you want to advise an aspiring researcher, would you tell them that, okay, don't look at transformers, look into something else, or will you say that don't work on language modeling at all?
I mean, I find language modeling very interesting. Of course, I would agree with Jan LeCun to say not to work on transformers, but to work on recurrent alternatives, such as the XLSTM. I think this is very exciting. And of course, the problem in language modeling is that you need a lot of compute. But we're especially working on this to make those language models more efficient and also have very good smaller models.
People have started using Mamba a lot. At least like we've seen A21, the lab that productionized something called Jamba. We saw a
Mhm.
company that is coming out of Mamba researchers, Cartesia. Do
Yeah.
you expect a similar trend with XLSTMs, or how do you see it?
Yeah, sure. And also, like not me, but Seb, the inventor of the original LSTM, has started a company called NXAI, and we are also working especially on this. So we want to scale it up in the company, build a product with the XLSTM, and want to show that it's really usable for companies and build on it. And yeah, maybe at the end, or the idea would be that to demonstrate that the XLSTM is even better on transformers on large scales. And for that, we need a lot of compute. And I think with the company NXAI, we're in a good shape to deliver this compute and to bring these large XLSTMs to life.
And transformers are like very popular now, and a lot of these companies have started using transformers. Everybody is looking into only transformers. What do you think it will take to convert these people from transformers to other architectures?
Yeah, I think as what I just mentioned is that we need to in order to convince those people which are really locked in into transformers right now, because transformers, they have been shown to be very well perform well on multimodal tasks even. And to convince those people, we have to show that XLSTM can achieve same performance or even better, more efficient, with less compute. And if we do so, I think then people will start switching to other models. And as you mentioned, people are already using Mamba a lot. I think that is the reason for that is that Mamba already open sourced efficient kernels, which makes it very easy for people to train Mamba models.
So that is like almost the direction that you just mentioned, to train bigger models to test the scale and also to write efficient kernels.
Exactly. Yeah.
And if let's say XLSTM, and we saw the graphs, let's say Mamba is there, XLSTM is there, and when people are looking
Mhm.
at alternatives, why do you think somebody will want to use XLSTM over Mamba?
Yeah, I mean, we show in our paper that we are performing better on language modeling than Mamba. So I think that is a good reason for people to use XLSTM instead of Mamba. But of course, what we aim to show is that we also see that we have this strong length extrapolation capability. And a task that is really cool is that when we show that XLSTM is better on handling long contexts, even with this fixed state size than Mamba, that would be, I think, a big argument in favor of the XLSTM.
I hope you enjoy the show. See you.